like for the previous couple of classes, just for from couple of you guys. And that is where my question starts. Like, how is it going with the problems? Like, it would be nice if you give me some personal answer, probably not very short, here or on WhatsApp, uh, preferably in personal messages, so that you can address exactly what are your difficulties, what are your challenges in studying geometry mostly, and like more precisely in studying these problems in doing them. I know that, for example, combinatorial geometry in principle is very difficult for understanding, for dealing with. So it's quite okay, quite normal to have difficulties. It is even useful if you not just have difficulties, but if you realize your difficulties and you can address them correctly. So let's discuss some solutions of the problems of the previous classes, of the previous class, first of all, and then we gradually shift to some new things. So there was a list of combinatorial geometrical problems, and first problem probably I will keep for you, so that you can try, like if you didn't do that so far, you can try it and you can use it as some material for discussing with me. But in principle, I will give you sort of a hint that this is very concrete, maybe very straightforward problem. So you just literally construct those five. You can literally construct such five rectangles. No, I would say general form difficult statements here. Just some observations which start if you do some experiments. So you take like 10-15 points on the plane and you try to reasonably cover them, and that's more or less it. Speaking of the second problem, I can call this sort of preparation for Hillis theorem. So we do something and like not we do something, but we have some construction so that it reminds us intersection of figures on a plane. But in this situation, it looks more like intersection of one-dimensional figures, right? And that is actually one of the possible generalizations. So Hillis theorem is true in any dimensions starting from d equal to 1. So it literally starts from this statement. But they are sort of not particular examples of one of another. They would be just similar things, and they could be proved or could be done in an induction. Yeah, I don't remember the details now, but I believe that like this d-dimensional case could be done just by induction if we know already three-dimensional case. Actually, I cannot guarantee that for sure. But what I can tell for sure that this is two-dimensional case, and in 2 dimensions, as you can see, less information would be enough for proving that they might be I believe it's called pegged. So like they could be pinned with a single point, like all of them. Yeah, we have this. So the straight line and the segments. So I draw it like this, but in reality they are like line one on another. And this problem is quite good for illustrating one quite important principle, which is used for proving many combi geometrical problems. That would be like in different interpretations, that would be called bottleneck principle. Or sometimes it could be referred as extreme element principle. Just one sec. I will double check our interpretations. Yeah, I believe it's normally referred as extreme principle or extremal principle in English, or bottleneck principle, or something like edge element principle, or like something which shows or which reminds us that we must choose elements from the I would say perimeter of attention, like being on the edge of what is interesting for us and not interesting. What is the direct implementation here? Or in other situations, the direct implementation is that oftentimes in very chaotic, with lack of structure data, it makes no sense considering just the average object. It makes sense just considering something which has extra properties. Either it's an object geometrically being in the extreme position, the most left position, the most right position, the most top position, the most bottom position. In other situations, that may be some other extremal value for the parameter, like the largest area, the longest segment, whatever. And then by considering such objects, we like add additional properties to our consideration, because we'll be dealing with an object which has that properties by the choice. How it is implemented here? So it is implemented in the following way. We will consider the segment with, I would say, the most left position and the most right position. And they must have intersection still, because like they either do coincide somehow, or they do intersect by the conditions. What remains is well defining of what we want to do, because when I say that, if I say, let's consider the most left segment of the set, it's not quite clear what is that. Like, maybe from the point of view of common sense, it may be understandable, but from the point of view of mathematics, it's absolutely not usable, because it's ambiguous. It has several meanings, or it may have several meanings with the absolutely same phrase, absolutely same formulation. So, for example, we may consider as the most left segment the segment with the most left gravity center of all the segments which are represented, right? So we just say that, okay, we will measure the position of the segment by its middle, by its midpoint, which makes much sense, right? And among such segments, like among these segments, we consider the one which has like the most left position according to these metrics. But also, not also, but like what we can see then is that if we consider different situations, then our intuition of the most left segment may be sort of violated with some different real situations. So for example, here, the most left segment would be this one, right? With this definition. And this one, which also makes much sense to consider as the most right one is this. Let me change this so that it is coherent with the phrase. So we may have a situation when we have a longer segment, which contains entirely this most left segment. And then we have a situation like this, that actually not the most left segment contains the most left point of the set, right? And it depends just on the situation. What exactly do we want to consider as the most left segment? This one or this one? But what definitely could be said is that both of them fit the role of most left segment, just by different definitions, right? Why is that? Like, how come? How come we can say that some segment is the most left segment without any troubles, like without additional complications? The thing is that there is just no genuine and well-defined property to be the most left on a plane. Like there may be some different understandings of that, and this notion is just not well defined for arbitrary objects. So terms like the most left item are not well defined for arbitrary figures. On plane. And for what it is defined then, right? So first of all, there is no left and right on a plane in principle, unless and until we consider a system of coordinates. So left and right are defined just when we have a direction. So from this point of view, normally left, right, and also up and down are defined by a system of coordinates. In natural way. So we literally say that, okay, guys, let us have a system of coordinates here, or at least x-axis. And then we say that like with just x-axis, it actually works quite not well. Because what we do next, we say that, okay, what is the most left point? Because the thing would be well defined for points. So we say that, okay, point, we consider point to be the most left if its x coordinate is less than all others, right? So we have here x1, then x2, x3. And we say that the most left point would be with the least x coordinate. But the least x coordinate couldn't be defined solely with the x-axis. And that is sort of news for today. Like if we have skew system of coordinates, if we don't suppose by default that it is orthogonal, then the second coordinate line, it may be skew, of course. And that means that in this situation, if we have direction y being slightly modified, like this, then the most left position according to this y coordinate would be y prime. So according to system of coordinates x, o, y prime, like involving this line and this line as coordinate lines, x2 would be the most left position, right? But if we take the standard orthogonal system of coordinates, then x1 would be the most left. So this shows that these terms, directional related terms, left, right, up, down, and probably some others, they are more difficult than they may seem. And that means that you should be more attentive to them. I saw like tons of mistakes done because of some misunderstanding. The student's own solution, which was worded with these terms, left segment, right segment, without specifying. So the guy, like normally student has some idea what to do, tries to do some proper realization, but without providing pure and unique understanding of these directions, how exactly he chooses some extreme element, he would confuse something himself just in a bit, like would do several paragraphs of text, and then all of a sudden will make a mistake by involving alternative understanding of the term. Okay, so coming back to that problem about segments, I would like to consider probably not even the most left position of segment, but I will consider segment with the most left point among all the points on the plane. No. Just one sec. Like what I first, like in order to understand what I'm thinking about, why I'm not telling you just the pure solution and why I spend so much time for such clarifications, like in order to understand this, you must know and understand clearly just one simple idea. I'm perfectly convinced during like my training ages of training others, and before that my personal training, like how I was trained, that trainings for solving and trainings for, I don't know, knowing mathematics, they are different. So oftentimes we made trainings for knowing mathematics. And that is something broader than we probably can understand now, because we do remember something, but we don't have this I would say utility of the knowledge. Like we cannot use it. There is some clever term for this. I think that would be some sort of intelligence, and like that is not very formal, but still quite useful term about like some sort of intelligence when we do apply something that we know. So I can easily tell you the solutions of those problems because, like, first of all, I was collecting them, right? So if I don't forget some details of some problem, I saw the solutions for like 10 times at least for each of the problems. But the thing is that it wouldn't push you towards solving such problems yourself. And I'm trying to speak out, to verbalize such subtle matters which really are used when you think of a problem before you start understanding which methods you can use. So you have the problem, you have the task, right? You understand what you want to do, to prove, to solve, and so on. And you have nothing more in principle. So you have no theorems about that situation. You have no knowledge of such situation. You have almost nothing. And what you do then, and it turns out that you do quite different things in different areas of mathematics. So you saw that I have my personal sort of to-do list for classical geometry, and it turns out that I have sort of similar to-do list in combinatorial geometry. These two quite unexpectedly would be intersecting by the parts where we draw the pictures. So this would be really geometrical sense of of the problems, and it would be like some additional attention would be spent on this in both cases, but with different accent. In combinatorial geometry, the accents would be slightly different. So I literally pass you through the ideas which we try to notice or recognize when we do try solve such problem in unknown surrounding. So in unknown situation. So here, what I'm trying to explain is actually sort of emerge of what we have as mathematicians, and that is mathematical intuition, mathematical sensation, right? All of us, if we do mathematics on high level, we do have that special thing which others who are not professionals, who are not in this area of activities, they most likely don't have it. And that would be informal following of some ideas of your inner voice, like there are different descriptions of that. And the thing is that some people confuse this with the mathematics itself. So instead of doing mathematics then based on these particular noted things, based on these particular ideas which emerged, based on these very thin, subtle sensations, I would say, which you have regarding this situation. People like stop on this part. They write this as a story that, okay, we do this, we do that, and most likely we have this. And they never touch the real mathematics because the real mathematics starts where solutions start. So there is no mathematics without solutions. And actually, there is no solutions without writing down the solution and giving it to some other professional so that the professional can read, can verify. Like many people who are talented, even talented in mathematics, they never cross this line. So this becomes a professional threshold. So when I say to you that what I want to do here, I literally touch this very strange area, right? Like what do I mean when I say what do I want to explain, to consider here? Like, isn't that just proof? The truth is not. It's not just proof. It's your approaching that moment, you formulating that for the proof. So what I want to consider is actually the most tight or most limited construction in this in this problem, with the most tight constraint. So here we can intuitively say that, okay, if there is some other segment which would be intersecting in this manner, like we will call these segments 1, 2, 3. So here we can see that intersection of 1 and 2 is sort of our area of interest, because it's area of intersection where we can put the point, the common point, which would be intersecting some of the segments, or if we are lucky enough, all of the segments. And we have sort of conflict or competition regarding such area of different segments. And my idea, or what I notice here, is that if I put another segment, like third segment here in this position, visually this position, like without explaining at the moment, it would be sort of biting just a part of this area. So it will be limiting this area of interest to some smaller area of interest. And trying to formalize this intuitive understanding, intuitive, maybe even sensation, I say that I'm interested in this thing in the left end of the segment, being in the most limited position, being in the most right position. Most right position. Of the left segment or left endpoint. And what I say here, what I claim, is that considering such things is almost impossible without proper mathematical writing, even in your draft paper. So if you don't write this phrase, most likely you'll be understanding what you do here intuitively. And as the intuition is not straightforward here, it's, I would say, 2 steps intuition. Like the construction of what we are interested in, it is 2-step thing. And like, you can trust me or can not trust me, but even in this problem, I saw like probably hundreds of mistakes, like mistakes by hundreds of students, because I was given it in classes and discussing with them on some trainings for competitions. So if students do write such definition to their draft paper or white paper, whatever, they have a chance. They have quite good chance actually then. If they don't write these, almost no chance to do that mathematically strict. So this would be the exact borderline, right? Those who write, they most likely succeed in this problem. Those who don't write, they don't succeed in this problem. So I urge you, I beg you, like, please write such things, write such definitions. Otherwise, you will limit yourself. Like, you will limit what you can do just by the depth of your operating memory. And okay, like after discussing that this is sort of intuitive choice, which though may be strictly formalized, let's complete the formalizing. So I understand that I'm interested also in the similar thing with the right endpoints of the segments. So what I say now is that let's consider this a segment with the most left right end. Right ends were here, like I denoted it with blue color. I will throw a note regarding that to the text a bit later. So let's consider a segment with the most left right end. Segment first, segment S1, and a segment with the most right left end. Segment S2. Here, it's also quite important what I write, that it's segment S1, segment S2, because in complicated situation, like how can we deal with this in mathematics? We do process things into intellectually, right, in our head. We cannot put them to the hands and hold in most situations because it's information in our heads and like in text. It's not physical in most situations. So imagine you have some quite complicated object in complicated situation in mathematics. Can you, I don't know, put some support on that? Can you, I don't know, maybe wrap it with some film so that we preserve the form of the thing and like we keep an eye on the object so it stays safe and stays, I don't know, in the initial form and state of quality. Like we cannot do such things, right? But we want in quite many situations we want still to deal with complicated objects in mathematics, and we want them to be same during the process of solving. For example, we don't want to lose the exact understanding, for example, of the shapes of the object. Like we may be interested in preserving exactly the same thing, right? How we can do that? Like if we don't have, if it has just some complicated definition and don't have a shorter name, my claim is that we, in most situations, will be just skipping working with the object properly. Why is that? Because we cannot process it in natural way. Like each usage would be involving pronouncing the entire definition or almost entire definition, and sometimes the definition is like it's just sequence of constraints. So we consider number such that it is, say, integer less than 100 millions, like, I don't know, prime having remainder 1 modulo 3, and so on and so forth. So sometimes we have objects which would be having like 5, 7, maybe more parameters. And when they are united all together, we have that object to consider. So if we don't have a title for them, if we don't have notation for that, we don't use them. And that is another sort of unexpected but very truthful rule. So it's not mathematical rule at all, but it's empirical rule. It's practical. It follows from practice. So those who don't define, like don't give a title for a complicated object with complicated definition, most likely wouldn't get use of that definition. So even if I do pronounce this definition here, I have still many opportunities to not to find the solution. I can not write down the definition. I can not formulate it properly. I can give no name to the segments, and like all these things are sort of on one hand professional tips how to do, but on the other hand it's just I would say naughty advices how not to solve a problem. So if you don't do that, you just don't solve. So again, like suppose we have segment S1 and S2. Reminder for us, this is blue end, this is red end. And now we are ready to do some mathematics, like just now. We say that, okay, after this consideration, S1 and S2 do intersect by their conditions, right? So the question is, so they are situated on the line somehow like this. Still not taking the picture too serious because, for example, it's possible that the entire, I don't know, like probably some study would be done, but what we can say that any other blue point would be to the right from this one, and any other red point would be to the left from this red point. Then the claim would be then any other segment intersects the intersection, like contains the intersection of these two segments. Actually, S1 and S2 may also coincide. Then any other segment contains it. Okay, why is that? That is actually by very natural observations, because we consider any other segment, its right and would be at least on this level of the most left right end. So any other end would be at least on the same position or to the right, right? So if we consider any other segment, its right end would be sorry, to the right from this point. Its red end would be to the left from this point. And in principle, that means that the entire this segment would be contained by each other segment. So actually, the proof part would be extremely short then. I would say that mathematical part is this, but this is something related to mathematics. And this related or meta-mathematical part would be rather bigger. Okay. Let's probably do a small pause. After that, we take just some brief solutions of a couple of problems, and we discuss new topic. Maybe even not the new topic, but new subtopic of combinatorial geometry. So now we have break for 5 minutes. Okay, 1, 2, 3. Let's consider. Oh, let's continue. Pardon. Let's continue with other problems. By the way, if you have any requests about considering some previous problems, please let me know. Probably today we will have some time for that. Yeah, like one dimension, 3A. 3A. Did we complete the proof of Halley's theorem? I thought that we done almost entirely and just probably details remained. But is that correct? Yeah, I feel like it is considered as solved completely. So 3A we did in class previous time. 3B, can you hear me, guys? Is everything okay with sound?
Yeah.
Okay.
Okay.
So 3B, I remain you for practicing because it would be following almost same structure. And moreover, after proving it for 3B, feel free to generalize that for higher dimensions. That will provoke you thinking of many different mathematical things. So first of all, what is like four-dimensional version, for example? How to understand that, how to deal with that. Just to open a small secret, like me being a geometer, uh, like by my primary mathematical occupation and dealing with abstract d-dimensional geometry and d-dimensional polytopes, like for example in my thesis, I still cannot imagine that in the full understanding of the word imagine, like that geometrical situation. So I know many different properties of that. I know some interpretations, but I have no clear vision of how d-dimensional picture looks like, or at least should look like. So that is very abstract saying that somebody understands how like four-dimensional thing looks like. And those who say that, okay, look, it's tesseract, the four-dimensional cube. By the way, if you didn't know, tesseract is exactly a name for four-dimensional cube. And like that is like somebody would say that, okay, and this is the way how we imagine or how we see four-dimensional cube. That would be either not understanding how it works in principle and just hearing something and then passing the information without deep understanding, or maybe even tricking you a bit. So probably the person realizes that this is not the not the whole image of the situation, but it would be just convenient for that person to say that, okay, and this is how we imagine it. So you will have an opportunity to think of these matters if you consider like not 3B, but sort of 3C, right? Extension there. Problem number 4 would be quite nice exercise for problem number 3 for Helly's theorem. And let me tell the solution right now. Because this one I like badly, meaning like I like it really, really much. So it's problem number 4. We have this 7-gon or heptagon, and we consider pentagons with the vertices in these 7 points. So say this one, like with these vertices, then these vertices, and say these vertices, which allows us to draw corresponding polygons like this. Like this. And like this. So on this picture is quite trivial that there is an intersection of these 3. And absolutely not clear what about the general situation. So what would be the limitation for drawing these pentagons, especially accounting for the fact that I drew this as almost regular heptagon, at least close to regular heptagon, but it was never mentioned in the task. So actually the heptagon may be very ugly. So it may be very irregular, not like here. And it adds some new levels of not understanding how it's happening. But if we recall that these are convex figures, convex pentagons, and we need to prove that convex figures share a common point, we might be interested in trying, in applying Helly's theorem. So for Helly's theorem, we must check this property just for any 3 of the objects. So that is like huge limitation, or not limitation, but huge relaxation. Instead of proving that all of them are intersecting, we may have this reduction to the situation when just 3 are intersecting. And this is something doable for many different situations because parameters of three objects is easier to catch and easier to maintain than maintaining same parameters, but for arbitrary large set of such elements, right? So here the question is it true that any three, is it true that any three of that pentagons have a common point? And this would be, I like badly such reformulations, because this question is a particular case, right? It is just part of our initial statement. Our initial statement is proving that all of them. Here we do try proving that three of them like share something. But still, Haley's theorem allows us this lift up in automatic manner if we prove just this reduced version. So I call this equivalent reduction of a statement. And equivalent reduction is probably the sweetest thing you can imagine when you solve a problem. Equivalent reduction. I can tell you sort of the value of such equivalent reduction or the real use case. I do like checking problems on such equivalent reduction or something close to equivalent reduction, like easy sequences, consequences, or vice versa, possible reasons why, in sort of fast way. So when I read the task, like I have this Olympiad habit, or at least I had this Olympiad habit to read all the tasks during the first hour, because the questions are allowed on IMO, or at least were allowed. I don't know about right now, but most likely still the same. So the questions are allowed during the first hour. And that means that if I want to use this opportunity wisely and to the full extent, I need to be ready to ask questions, not just about the questions which I'm reading and solving right now. And problems on IMO are of such difficulty that even the first problem may take arbitrary time. It may last long or take long time. That means that if I rely just on the problems which I was thinking about, I may be late with my questions when I'm ready, right? So I do read the tasks. I spend for each problem maybe 10-15 minutes, and I try to do the more thing the possible during that 10-15 minutes, even though the problem may be very difficult. It may be last problem. So exactly that situation happened on the first day of IMO where I was taking part. I was reading the tasks, and from the point of view of reading the tasks, like it's almost no difference in which order you read the task, because you like I'll be giving myself 10-15 minutes, right, for that problem before switching. So I started from the third problem because it was inequality, quite similar to what I like. I was understanding that probably I will be able to apply some basic techniques, probably Murhead, probably um, some homogeneous ideas, like some ideas about symmetry of the variables. So I did one equivalent reduction. So like I twisted a bit the task. I did equivalent reduction. I was quite happy because it's like the third problem of IMO, and like it's quite cool to do that within, like, to have some progress within 10-15 minutes. But I proceeded, I continued because it was just first several minutes, and I did another equivalent reduction. So after the sequence of probably 3, 4, maybe 5 equivalent reductions, I remained with really completely different inequality, which looked rather more natural, and I was understanding that it is like most likely is solvable with techniques which I know, which I have like in my skills. So I completed that problem in another like 15 minutes. So like I completed with reading, so I switched to something else. I didn't solve the problem from the first glance and like from the first line of these equivalent reductions. But when I switched back after reading all the tasks and like asking the questions and all this stuff, I spent another 15 minutes and like the third problem was done. So equivalent reductions is what you really want to have in any sort of problem on competition. It is possible, like it's not related to some branch of mathematics, like in inequalities, geometry, like whatever. It's uniform for all mathematics, and if you have that, oftentimes you like you know that probably that will cause some points. So that is what you want, what you really want on competition. And oftentimes that would be just reducing the difficulty, the complexity of the problem. Okay, so here, instead of solving the problem for arbitrary n, this technique with Helly's theorem, it first of all suggests that we should consider just 3 of the n. But okay, we have 7 vertices, right? We have 3 polygons, 5 like I will write 5 gons, right? Pentagons. So how many incidences of vertices they generate? So they technically generate 15 vertices in consideration, which actually not vertices, but incidences, not incidences, but yeah, probably incidences. Incidences of vertices. So when we speak of a vertex incident to, we don't say that normally. Like we say that vertex incident to an edge, but here we would say that vertex incident to a pentagon. So each pentagon generates 5 incidences then, right? And in total 15. That means that there must be a vertex with incidence 3 in these 3 pentagons, right? Which means it belongs to all 3 of them. Why is that? Just because if not, then by considering the contrary, each vertex has less than 3 incidences, not more than 2. We have that the maximum amount of incidences then should be 14, or doesn't exceed 14, which contradicts with the fact that we have 15 incidences. So we proved that 3, they have common point, and then some students have this reflex, like, let's continue by induction. But actually, we should, and technically they would be passing the path of proof in Helly's theorem once again. But we don't need that, right? We just refer to Helly's theorem. We say that okay, among this set of convex figures, it doesn't matter much here that there are polygons in this part. So in the set of convex figures, we know that each 3 have common point. That means that all of them have a common point. That's it. So this is very symptomatic. Kelly's theorem allows this equivalent reduction in many situations, or at least it may be related to equivalent reduction. Okay, these two problems, they actually oftentimes go separately because one of them is classical theorem from combinatorial geometry. Another is a problem from some Olympiad, maybe 20 years ago. But in reality, they are sort of inverse problems of each other. But for understanding this idea of inversion, I would like to to first consider the 6th problem. Oh, not 6th, but 7th problem. Because it would be pure idea of the dual usage. So probably, yes, probably I will tell the 7th problem, and these 5 and 6 will remain for you for further thinking. And then I will mention some new problems and like some new topic. Actually, like that would be topic of extreme element approach, which we discussed for like half of the class already. So it was something we already discussed. Finding the family of lines in the plane is given. It is known that any 3 of them can be intersected by a disk of radius r. So we have family of straight lines. So yeah, like the word straight lines are missing here, but without that word, this problem makes no sense, I believe. So we have family of lines, of straight lines, And we know that any three of them, though they may be not intersecting altogether, but they may be intersected with a single circle of the particular radius r. So this situation looks like this. The question then is that is to prove that all of them can be intersected by a disk as well. This problem involves some sort of duality or duality. Where by duality we understand similarity of relations. Which duality probably you are familiar with. Probably you are more familiar with this sort of duality when you consider plane graphs or planar graphs. There is a method how to create a dual graph. So we do put a vertex of a different graph inside of each face of this planar graph drawn on a plane. And then we do connect the vertices corresponding to the faces, which are neighboring faces. So we have this sort of diagram there. So in this diagram, we get again some plane graph or planar graph. It would be realized on the plane already as plane graph. So it will be having no intersections if drawn everything well. At least it's always possible. And we will have its natural correspondence that in each face of this new graph, we'll have a vertex of the initial graph. So actually, if we also take external face, infinite face, into consideration, we will have rather more like the structure will make more sense, but it will be a bit more complicated drawing. So this is sort of duality, which you, I suppose, probably know, or I estimate that you most likely know. There are also other types of dualities. When you have relation between some types of objects in a problem, and you then have that opportunity to sort of inverse that, take some sort of reversed version of that relation. So here, with some combination of straight lines and, for example, circles, such duality also exists. There is some sort of standard duality for this case. So what does it mean that straight line and a circle of radius r do intersect. That means that, like, some obvious thing happens. If we draw this distance from the circumcenter to, like, if we take the circle, center of the circle, its distance to the straight line would be less than r, less or equal. R is less or equal than, no, distance is less or equal than r. But then we can reformulate this. We actually then can do following. We take absolutely same situation, but now we'll be considering some different property of it. Let's consider our how it's called, our neighborhood of the, or our surrounding of the straight line L. It actually would be just a strip, infinite strip of width double r, right? So we take r to this side, r to this side, and instead of the center of circle, we consider, instead of the entire circle, we consider only its center. So the statement then is that the circle, or observation, because it's quite simple statement. The circle, no, let it be gamma instead of omega. Gamma is in Russian alphabet, so I can use my keyboard. So the circle gamma intersects the straight line L if and if only its center C belongs to the R neighborhood of L. Why is that? But, like, it's very trivial, right? The circle intersects the line when the distance between the center and the line is less than r, less or equal than r. And the point, the center of the circle, belongs to the strip if its distance to the line doesn't exceed the same r. So we have a technical description of these two situations being absolutely same. So they do they are satisfied simultaneously, or they are violated simultaneously. So if a circle doesn't intersect, probably it should be the second part of the claim. If a circle doesn't intersect a straight line, even by a point, then the center of the circle doesn't belong to the strip. So now let's reformulate the dual problem. So the dual problem, a family of strips with double R are given on plane. Each three contain a common point. Show that all of them have a common point. Right? So if we want to show that all the straight lines could be intersected by the same circle of radius r, that means that their strips or their neighborhoods all must contain the center of that circle. So we have this neat reformulation. Okay, but now I bet you already understand what happens. Like we have the situation when we have a finite number of infinite strips. Quite easy to check that a strip is convex figure because with any 2 points, it contains the entire segment between them. And for these convex figures, we do apply Helly's theorem, and we basically get the result. So no miracles. So then, by Helly's theorem, and this is somehow similar, or at least reminding what's happening in problems 5 and 6 about circles, polygon, Jung theorem, and so on. Probably I misspelled Jung. I will double check a bit later because it looks unfamiliar actually. Okay. What's next? What did I want to discuss with you? As a part of new material. So actually, it would be not new material, as I mentioned previously. It would be more training, directed training in applying this extreme element principle or bottleneck principle. One of the classical problems where it is applied would be Sylvester theorem. It says that suppose a finite family of straight lines is given on plane. Then either there is a point of intersection of exactly two of the lines, or at least like find a family of n straight lines. Or at least n intersection points. If I'm not mistaken, let me double check, and you can try solving it, like try finding some ideas about such situation. No, like the classical formulation would be slightly different. It's just a problem, which would be one of the problems, and I will double check the number n here. It was not quite clear what to do if several lines coincide. So like I will double check the formulation here, but the Sylvester's theorem would be sounding in different way. Suppose that a finite number of I will write first the original version, and then it would be not reminding this, and then I will write down the dual version, which would be reminding this. Finite number of points is given on plane. So that each straight line passing through two of them also passes through a third point. Prove that all these points belong to a straight line. So this is quite an unexpected formulation, I'd say. And then speaking of dual formulations, we have a dual problem, which would be starting from a set of straight lines, I believe. So you can start thinking about the first problem, the Sylvester's problem. I will write another formulation, and after that, we will discuss a couple of ideas which may be useful here. Okay, so here, what you can read next is the dual formulation of the problem, which would be a result of substituting straight line by point, point by straight line, and preserving incidences. It turns out that there is geometrical transformation, which we didn't have time to mention much. I probably mentioned it just a bit, but even didn't do any claims on that. So probably we will discuss that during the next class, which would be, I believe, the last one of our series of classes. So I believe that would be quite nice topic to end with, and it would be having impact on the fact that you can consider such dual structures in combinatorial problems, which even if you don't apply that in pure geometrical problems, might be useful for combinatorial geometrical problems. So that is the bigger plan, and the smaller implementation is that these two problems you can observe and you can compare. They are in this dual relation. So the Jung theorem and another problem from the previous list, they are also in dual position in some sense. So you can compare these dualities. All of them are called referred to as dualities, called in some informal way. So you can try comparing them. And here, together with these problems, I would mention one other problem which may be more familiar to you, having slightly different shape, I would say. So another problem is that any possibly not convex polygon without self-intersections can be diagonalized, I believe. So divided by diagonals. It could be triangulated. The classical version would be triangulated by diagonals. So another classical result is that if we have if we have a convex polygon, it is almost absolutely clear that any polygon would be diagonalized. We can just draw these sorts of lines from one vertex, like diagonals, to all other vertices to which it's possible, and we are done. But if we have some strange situation when a figure would be bounded with a broken line without self-intersections, then if it's having no self-intersections, that means that by a famous theorem, it would be dividing the plane into three parts: the outer part, inner part, and the boundary part. Also, the boundary would be consisting of straight line segments, just by definition, that it was bounded by broken line, like obviously closed broken line, like coming to the starting point. So in this situation, we may be also interested in the diagonalization. And here it's not that clear how to systematically explain that it could be diagonalized, because, for example, if we try to apply this construction here, then starting from this point, we just cannot draw most of the diagonals. We can draw diagonals just to this, a diagonal, just to this point. But if there would be no point here, if this side would be connecting a vertex here and a vertex here, then we would have, in principle, like no, like it's still like there would be then no this vertex, right? So like some questions appear immediately when we try to do that. Try to consider some direct process of diagonalization. The question would be why it's doable. In all these problems, the key to solving the problem would be lying in considering the extreme element. Like it would be quite clear that we should be referencing to this somewhere, but the implementation of this idea may be not that clear. So, for example, if we spoke of left segments, right segments, most left segments, like how do we apply these, for example, for this situation with diagonals? And the key is that we should be considering objects with some parameter which is measured normally, and with the extreme value of that property. Of that parameter. So that may be x coordinate, right? So left, right. That may be area, smallest area. What else? Length. And actually, so on, right? Because any numerical parameter could be used like this. Not just numerical parameters could be used. Also, we may use boundary elements in geometrical sense. Geometrical or any other. For example, there is such object which is called convex hull of a set. We consider the least by inclusion set of points on plane which contains the given set. So here it will be convex hull. And some elements of convex hull may be used as extreme elements just by geometrical meaning. They are belonging to the boundary of the set. They by default they have some special property because of that. Okay, you try solving this, and I suggest you to send me more messages about like the process. Yes, like sometimes I have hard times with time, and like not always I can answer in sort of fast manner. Probably I'll be able to answer you sometime later after ending of our classes as well. So I'm here more focused on the material which I give, right? On the ideas which I give. So take your time, try doing something like in the sense like try having some advance in those problems, or at least try understanding where you got stuck in those problems. And you tell me, like you write me about that, and I will try to guide you to the next advance point. And then when you have several advances in a problem, you normally solve it. Any questions?
And the second question about the set of lines, is it a finite set of lines or an infinite set of lines?
Once again, I didn't
The
understand the
second
end of the
question, a
question.
set of straight lines is given
Yep.
on the plane. Is it
Okay.
a finite set of lines or doesn't matter?
Finite. So it's like it's dual for this problem. So it's just preserving everything but the types of the objects, all the straight lines inverted to points and all the points inverted to straight lines. So if we had finite number of objects, it should be finite number of objects. So a finite set. Yeah, thank you. And here, everywhere, by like in combinatorial geometry, almost always, a line means a straight line, even if it's not specified. Any other questions? Okay, if no more questions, then we finish now. See you next time, and try considering also the previous problems, like which were before. If you didn't do that, if you didn't hear the solution of them, just try solving them and write me solutions. But if you cannot do that, if you fail, ask me questions. Okay, so that's it. Bye. See you next time.